Hi everybody, so this is going to be a work-along video for the final day of review. These kinds of questions will be on the test. Right, so for the first problem, for the reaction 2H2 plus O2 yields 2H2O, 5 grams of hydrogen react with 20 grams of oxygen, what mass of water is produced? Anytime you see two givens, 5 grams of hydrogen, 20 grams of oxygen, good idea to check for limiting reactants. So what we're going to do is convert both of these to mass of water. Whichever one is smaller, that should be the answer. To convert from grams to grams, you first have to take a look at the mole map, right? So the mole map says if we have grams of one chemical and we're converting to grams of another chemical, we first start with grams, then we convert to moles using the molar mass of the first chemical, then we use the reaction ratio to convert to moles of the second chemical, and then back to grams using the atomic weight of the second chemical. So, um, so here we're going to go from grams, first chemical, then to moles of our first chemical, then moles of water, and grams of water. You'll notice that for both of hydrogen and oxygen, if we actually convert to moles of water, this first step, we can actually immediately see which one is limiting because the final step, going to grams of water, just involves multiplying by the same number. But anyway, let's take a look. So 5 grams. So if we take a look at the periodic table, for hydrogen, that's 1.00794. Since we have two of them, that's about 2.02. Every mole. Get us to our first conversion. Second conversion is a 2 to 2 ratio for hydrogen to water. 2 moles of hydrogen on the bottom, 2 moles of water on the top. And then finally, for every mole of water, 18.0. If you do round these numbers to whole numbers, like use 2 grams or 18 grams instead, the numbers should be close enough. Okay, and so let me pull out my calculator to calculate this. So 5 times 1 divided by 2.014 times 2 divided by 2 times 18.015 divided by 1. That will get us 44.7 grams. On the other hand, right, if we take a look at our oxygen, 20.0 grams of oxygen, maybe this one is limiting, so we've got to calculate it the same way. So 32 grams of oxygen per mole of oxygen. Then it's a 1 to 2 ratio this time, 1 mole of oxygen for every mole of water. 2. And then finally times 18 grams. So 1 mole of water is 18.015 grams of water. And what we'll get out of that is, well, 20 divided by 32 times 2 divided by 1 times 18.015 divided by 1. That is 22.5 grams of water. In this case, the smaller of the two numbers, in fact, for all limiting reactant problems, the smaller of the two numbers indicates that oxygen, or indicates that that chemical is limiting. Oxygen is limiting in this case, and so you can only make up to 22.5 grams of water here. So a lot of these problems are going to follow similar formats, right? Being able to calculate how much product you're going to get, and then figuring out percent yield, percent composition from there. Okay. So for number 2, 12 grams of nitrogen, 10 grams of hydrogen, so we have to figure out how many grams of NH3 can form. So first, let's start with nitrogen. 12.0 grams of nitrogen times 28 grams of nitrogen is 1 mole of nitrogen times, if we take a look at the reaction ratio, it's a 1 to 2 ratio for NH3, so 1 mole of N2 gets us 2 moles of NH3 times, for every mole of NH3, we have 17 grams of NH3. So if I plug that into my calculator, 12 divided by 28 times 2 times 17 is 14.6 grams of NH3. And if we compare that to hydrogen, 10.0 grams of hydrogen times 2 grams of hydrogen for every mole of hydrogen times, here, this time it's a 3 to 2 ratio. 3 moles of hydrogen for every 2 moles of NH3 times, for every mole of NH3, 17 grams of NH3. So that will equal, so 10 divided by 2 times 2/3 times 17, that will be 56.7 grams of NH3. So it looks like we have plenty of hydrogen. What limits here is so we're only going to make 14.6 grams of NH3. Or number 3. So we have 8 grams of aluminum, 10 grams of chlorine. So again, a limiting reactant problem. 0 grams of aluminum for every 27 grams of aluminum. Our reaction ratio here, we are trying to figure out AlCl3, so that's a 2 to 2 ratio. 2 moles of aluminum, 2 moles of aluminum times a mole of aluminum chloride. It's, I believe, 133.33 grams. That equal, well, 8 divided by 27 times 2 divided by 2 times 133.33 gets us 39.5 grams of aluminum. From aluminum, if we take a look at chlorine, we have 10.0 grams of chlorine times. All right, so for every 70.9 grams of chlorine, we have a mole chlorine. Then it's a 3 to 2 ratio, 3 moles of chlorine for every 2 moles of aluminum chloride. And then finally, same step at the end, 1 mole of aluminum chloride gets us 133.33 grams of aluminum chloride. And if we put that into our calculator, 10 divided by 70.9 times 2 divided by 3 times 133.33, that is 12.5 grams of aluminum chloride. So it looks like that will be the amount. Chlorine limits in this case, we can only make 12.5 grams. Okay. For number 4, we have 16 grams of methane, 40 grams of oxygen. So again, 16.0 grams of methane. 4 times, for every 16 grams, we have a mole. It is a 1-to-1 ratio with CO2. 4 for every CO2 times 1 mole of CO2 gets us 44 grams of CO2. So if we do 16 divided by 16 times 44, that should be CO2 with 16 grams of methane. And if we take a look at 40.0 grams of oxygen, so it'll be 32 grams of oxygen for every mole of oxygen. Then here it's a 2-to-1 ratio, 2 moles of oxygen for every mole of carbon dioxide. So we're multiplying by 1/2 there. And then finally, times its molar mass. So 1 mole of CO2 is 44 grams of CO2. 40 divided by 32 times 1 divided by 2 times 44. That'll be 27.5 grams of CO2. I believe that is our limiting reactant, right? Oxygen is our limiting factor, so we can only make 27.5 grams of CO2. Next reaction, Fe plus S giving us FeS. We have 12 grams of iron, 12 grams of sulfur. How many grams of FeS form? So, right, again, standard procedure here. 12 grams of iron times. All right, so there are 55.8. Looking at the periodic table, 55.845 times, for every mole of iron, we get a mole of iron sulfide. That's a 1-to-1 ratio. Finally, for every mole of iron sulfide, that'll be 55.85 plus about 32, or 87 grams sulfide. So if we multiply 12 divided by 55.85 times 87.9, we get about 19 grams of iron sulfide, roughly. And if we compare that to how much sulfur we started with, 12 grams of sulfur times, okay, so we have 32 grams of sulfur for every mole of sulfur. Then for every mole of sulfur, we get 1 mole of iron sulfide. And then for every mole of iron sulfide, we have 87.9 grams iron sulfide. So 12 divided by 32 times 87.9 gets us roughly 33 grams of iron sulfide. So it looks like in this case, iron limits, and we can only make 19 grams of iron sulfide. 15 grams of potassium, 20 grams of chlorine, 15 grams of potassium times 39 grams of potassium gives us 1 mole of potassium. Then for every 2 moles of potassium, we get 2 moles Cl. Then finally, for every mole Cl, get 39.1 plus 35.5, that's about 74.5 grams Cl. Multiply all of that together, get 15 divided by 39.1 times 2 divided by 2 times 74.55. That's about 28.6 grams of KCl. And if we start with chlorine instead, 20 grams of chlorine times, for every 70.9 grams of chlorine, we get 1 mole. And then for every mole, 1 mole of chlorine, we get 2 moles of KCl. And then for every mole of KCl, we get 74.55 grams. So multiplying all of that together, 20 divided by 70.9 times 2 divided by 1 times 74.55, that's 42 grams KCl. So it looks like in this case potassium is our limiting reactant, so we can only get 28.6 grams of KCl. For number 7. So we've got 25 grams of zinc, 30 grams of hydrochloric acid. How many grams of zinc? So start with zinc. Table zinc is 65.38. 65 zinc. For every mole of zinc, 1 mole of zinc, we get 1 zinc. Finally, for every mole of zinc chloride, we get zinc was 65.38 plus chlorine's 35.45. Since there are two of them, that's 136.2. It that will get us 25 divided by 65.38 times 1 divided by 1 times 136.28. That'll be 52.1 grams of zinc. If we instead start with hydrochloric acid, 30 grams HCl times, so that's roughly 36.46 grams of HCl for every mole of HCl. Then it is a 2 to 1 ratio. 2 moles of HCl get us 1 mole of zinc chloride. Finally, every mole of zinc chloride gets us 136.28 grams of this stuff. Multiplying all of that together, 30 divided by 36.46 times 1 divided by 2 times 136.28 is roughly 56 grams of zinc chloride. So it looks like in this case, close, but zinc is our limiting reactant. Next, so we have 10 grams of iron, 10 grams of oxygen, right? So 10 iron times, so for every 55.85 grams of iron, we have a mole. For every 4 moles of iron, we get 2 moles iron oxide. And then for every 1 mole oxide, 159.69 grams of oxide. 10 divided by 55.85 times 2 divided by 4 times 159.69. That is 14.3 grams of iron oxide. And if we compare that to oxygen, that's 10.0 grams of oxygen times 32 grams of oxygen for every mole of oxygen times every 3 moles of oxygen get us 2 moles of iron oxide times for every mole of iron oxide we have 159.69 grams of iron oxide. And if we multiply all of that together, 10 divided by 32 times 2 divided by 3 times 159.69, that is 33.27 grams of iron oxide. So it looks like in this case, iron limits our reaction, 14.3 grams of iron oxide. Right? Next question. So we have calcium carbonate decomposing into calcium oxide and carbon dioxide. So here, oh, that's strange. 20 grams of calcium carbonate react with 10 grams of oxygen. Well, there's no oxygen here, so how could this problem be? Looks like we have an error. Can't answer. Because the question is malformed. Sorry, bad question. Okay, we'll just move on. 10 in 2 sodiums plus 2 waters, giving us 2 sodium hydroxide and hydrogen. 13 grams of sodium react with 36 grams of water. Calculate the grams of hydrogen produced and identify the limiting reactant. All right, so we got 13 grams of sodium According to the periodic table, 23 grams. Sodium, sodium. Then for every 2 moles of sodium, we get 1. Then for every mole of hydrogen, 2 grams of hydrogen. So if we do that math, 13 divided by 23 times 1 divided by 2 times 2, that's about 0.565. And if we compare that to the 36 grams of water we have, so 18 grams of water for every mole of water times for every 2 moles of water, we get 1 mole of hydrogen. And for every mole of hydrogen, 2 grams. So doing that math, 36 divided by 18 times 1 divided by 2 times 2 divided by 1, that is 2 grams of hydrogen. So it looks like in this case, sodium limits the reaction, and we can only make 0.565 grams of hydrogen. Okay. 11. So we've got silver oxide decomposing into silver. How many grams of silver form? Right, so we can answer this question. So we just start with 25.0 grams of silver oxide times, first we convert to moles. Silver is 107.8682 grams. So since we have 2 of them, we'll times that by 2 plus oxygen 16. That is roughly 231.74 grams of silver oxide for every silver oxide. Right, looking at the reaction, it's a 2 to 4 ratio. So 2 to 4 ratio of silver oxide every 4 moles of silver out of that. Finally, right, again, 107.8682 times for every mole. Every mole of silver, we get 107.8682 grams of silver. Plug all of that in. We have 25 divided by 231.74 times 4 divided by 2 times 107.8682. That gets us 23.3 grams of silver. 12. So again, a limiting reactant problem. Got 20 grams of C3H8, 18 grams of oxygen. Determine the mass of CO2 produced. So 20, 0 grams of C3H8 times, so 44 grams C3H8 gets us a mole C3H8 times, so it's a 1 to 3 ratio, 1 mole of C3H8 get us 3 moles of CO2. Finally, for every mole of CO2, that will equal is, calculations, 20 divided by 44 times 3 times 44 is 60. So C2. And instead, we start with 18 grams of oxygen, 32 grams of oxygen for every mole of oxygen, times for every 5 moles of oxygen, we get 3 moles of CO2, times for every mole of CO2, we get 44 grams of CO2. 18 divided by 32 times 3 divided by 5 times 44 is 14.9 grams of CO2. So looks like that's our smaller number. That means oxygen is our limiting reactant, and we can only make about 15 grams of CO2. Okay, 13. So we produce 36 grams of water, but the theoretical yield is 45 grams. What is the percent yield? So percent yield is equal to your actual, how much you actually produced, divided by your theoretical, expressed in terms of a percentage. So this will be the 36 grams that you actually produced divided by the 45 grams you were supposed to produce, and then multiply by 100%. So 36 divided by 45 times 100% is 80%. That will be our percent. The percent composition of each element in this compound, right? So, in total, this compound is 24.5 plus 70, or 94.5 grams in total. So that means the percent composition of nitrogen and the percent composition of oxygen. Well, for nitrogen, it's 24.5 grams divided by the 94.5 grams in total, expressed in terms of a percentage. So 24.5 divided by 94.5 times 100% is 25.93%. And then for oxygen, that'll be 70 divided by 94.5 times 100. 70 grams, 94.5 grams times 100. So that would be 74.07% PR composition. All right, for the next page. 10 grams of iron react with 12 grams of sulfur. Identify the limiting reactant. Because it's a 1-to-1 ratio, here's what I'm going to do. I'm just going to convert each of these to moles. So 10 divided by 55.85, that's 0.18 mole. 12 divided by 32, that's 0.375 moles of sulfur. Since it's a 1-to-1 ratio, that means that, hey, iron is going to limit the reaction because you need 1 mole of iron for every 1 mole of sulfur. That means for every 0.18 moles of iron, you need 0.18 moles of sulfur. That's what you have. You have plenty, but you don't have enough sulfur or iron in this case. Okay, to react with all of the sulfur. So in this case, the limiting reactant is iron. If you actually wanted to go through the calculations, you could figure out, okay, 10 grams of iron produces a certain amount of iron sulfide, 12 grams of sulfur produces a certain amount of iron sulfide. You compare, you should be able to see that it's iron. Identify the type of reaction. So, two chemicals combining together into one product. This is a synthesis. I'd balance the reaction. All right, so we got C3H8 plus O2, CO2 plus H2O. So let's see, we need a 3 in front of the carbon to balance the carbons. 3 in front of carbon dioxide. 8 hydrogens, 2 hydrogens, so we need 4 in front there to balance the hydrogens. If we count the oxygens on the right side, that's 6 plus 4, or 10. So we need a 5 in front of the O2 to balance all of the oxygens. So that should be 1, 5, 3, 4. Okay. Reaction theoretically produces 82 grams of sodium chloride, but only 64 are isolated. So the percent yield should be what you actually got, which is 64 grams, divided by what you theoretically should get, 82 grams, expressed in terms of a percentage. Nation. 64 divided by 82 times 100, that'll be 78.05%. Identify the reaction type. So we got one reactant breaking apart into multiple. That is a decomposition. All right, 15 grams of zinc react with 20 grams of hydrochloric acid. Which reactant is limiting? So we need to convert 15 grams of zinc to moles of zinc. So for every, let's see, zinc, 65.38 grams. Zinc, mole of zinc. Then it's a 1-to-1 ratio. Either product. Here I'm going to just choose hydrogen just to make my life a little easier. Doesn't matter. Both are going to scale up and down with how much reactant there is. Times for every mole of hydrogen gets us 2 hydrogen. 15 divided by 65.38 times 2, 0.06 grams. If we compare that to the 20 grams of HCl we had, so 36.46 grams of HCl is a mole. HCl times for every mole of HCl, 2 moles of HCl, we get 1 mole of H2. And then for every mole of H2, we get 2 grams of H2. 20 divided by 36.46 times 1 over 2 times 2 over 1. A 0.55 grams of H2, which means in this case zinc emitting reactant. The percent composition of carbon in C6H12O6. If you add all of those together, you're going to get 180 grams. So the percent composition of carbon is the 6 carbons that are in there, each of them at 12, gives a total of 72 grams of carbon for every 180 grams of substance, expressed as a percentage. That's 100, so 72 divided by 180 is 40%. Balance the reaction. All right, so I noticed that there's a 2 oxygen here, 3 oxygens over here. So to balance that, I'll put a 3 in front of the oxygen and a 2 in front of the O3. Get 6 oxygens on both sides. That's 4 aluminums on one side. I need 4, 3, 2. Type of reaction in number 23, that is a double replacement. You'll notice that the lead and the potassium switch places, so instead of lead with nitrate, it's now potassium with nitrate, and instead of potassium with iodine, it's now lead with iodine. Reaction has a theoretical yield of 12.5 grams of CO2, only 8.9 grams are produced, so percent yield is equal to 8.9 grams divided by 12.5 grams, what you actually got divided by what you were supposed to get. 8.9 divided by 12.5, expressed as a percentage, that is 71.2%. Right? Or 25, determine the limiting reactant. All right, so we've got 5 grams of magnesium. 24.3 get a mole. For every 2 moles of magnesium, you get 2 moles of magnesium oxide. And finally, for every mole of magnesium oxide, we get 40.3 grams of magnesium oxide, equal to 5 divided by 24.3 times 40.3 is 8.3 grams of magnesium oxide. And if we compare that to the 10 grams of oxygen that we need, 1 mole of oxygen, 32 grams of oxygen, then it's a 1 to 2 ratio. So 1 mole of oxygen gets us 2 moles of magnesium oxide. And finally, for every mole of magnesium oxide, we get 40.3 grams of magnesium oxide. That'll be equal to, if we do our calculations, 10 divided by 32 times 2 times 40.3, 2 grams of magnesium. So the limiting reactant is identify the reaction type. That would be a combustion reaction there. Percent composition of chlorine and calcium chloride. So calcium chloride, calcium's 40, chlorine's about 35. So in total, that's 110.9. Well, for chlorine, that'll be 70.9 divided by 110.9. Will be 64%. Balance the reactions. So let's see, because of the 3 and the 2 on the hydrogen, I'll put a 2 and a 3 there, and then that should balance the nitrogens. That is a double replacement reaction here. For 29, and for number 30, 12 grams of calcium, 30 grams of water. Determine the limiting reactant. So 12 grams of calcium times, for every 40 grams of calcium, we get a mole of calcium. And then here I'm just going to compare it to either one. It doesn't matter. I'll use hydrogen to make my life easier. 1 mole of hydrogen, calcium. Bottom for every mole. I'm going to leave it as moles. We can compare moles as well. 0.3 mole. 30.0 grams of water times 18 grams of water for every mole of water. 2 moles of water is 1 mole of hydrogen. That 30 divided by 18 times 1 over 2, that's 0.83 moles of hydrogen. So we're making less moles of hydrogen with calcium. Calcium has to be. All right, so long review, but hopefully that makes sense. All right, take care, everybody.